In the previous lecture, we stopped here. Okay, past year question 2015-16. This is related to gain adjustment. I actually asked you to look into it. Today we will continue with this, solving this question. A closed loop system is given with the transfer function. A dot plot with k equal to 1 here is also given. And we want to find gain margin, phase margin, phase and gain crossover frequencies. That we did last time. Before, we found that the phase crossover frequency is here at 7 radian. When it crosses minus 180 degrees here, so we get 7 radian per second. So at 7 here, 7 radian per second, this is the gain margin. The gain margin here is 26 dB. You remember, when the system is stable, then gain margin is positive. So we get 26 dB gain margin. And then we need phase margin. Before phase margin, we also need to find the gain crossover frequency. Gain crossover frequency is here. Okay, is where the magnitude cross 0 dB. So we found that it is at 0.8 radian per second. That is gain crossover frequency. Then we look into 0.8, here 0.8. Then the difference between the phase at 0.8 0.8 radian per second is here is 76 degrees. Here about 104 degree. Then we take the difference. 76 degree is the phase margin. Right, that for number 1. Then number 2 is regarding steady state error. Okay, remember steady state error is obtained. Here I mentioned I show before, the one I circled in blue here. Okay, for a first order system, for a system type 1, if we make a line, straight line from the original line, which is a straight line, then the one that cross 0 dB is equal to kV. So we make here on the graph, we make a line here, then make a line that cross 0 dB. Somehow the one shown here is already a straight line that cross 0 dB at 0.8. Then 0.8 here is kV. Okay, so we can calculate error. Error is 1 over kV, 1.2 error. That question B. Then we need to, question 3 is explain how the open loop frequency response can be used to estimate the time response specification, such as percent overshoot of closed loop system. This question wants you to relate the dot plot with the time response. Okay, you can refer to the previous note. We can relate, for example, phase margin with zeta, and also, of course, with percent overshoot. We can relate dot plot with stability. We can relate dot plot with time response, with the speed of the time of the response. You can see notes before. Okay, let's move to number 4. The control system now is required to operate at 20% overshoot. So now we want 20% overshoot. This is an example in which we can relate the plot with a time response in a closed loop system. Okay, we want 20% overshoot. Design K. Here, K. We want to find K here, the one I circle in the block diagram. We want to find K here to achieve this objective. The objective now is to get 20% overshoot. We know that from this graph, we can relate overshoot and also phase margin, because overshoot can be related to damping ratio, and damping ratio is also related to phase margin. So it can be, there is a relationship between both phase margin and also percent overshoot. I think I mentioned this many times because these will be used many times in design. Later in lag compensator, in lead compensator, also use relationship between phase margin and also overshoot. Again, this graph will be given in the exam, so you don't have to remember. If you check your notes, there is a formula between overshoot and also phase margin. Between phase margin and damping ratio. Then we have damping ratio with percent overshoot. Okay, from our initial study, when we discussed the original system, the phase margin is 76 degrees, right? 76 degrees. Then we know 76 degree is here, 76. Then from here, we almost 6 is here, is about 0.9896 zeta. Zeta 0.96. You can see here zeta 0.96. Okay, about here. The overshoot is almost low. Okay, about 0% from the graph. So the initial one is already good, because phase margin is quite high, 76 degree. Zeta 0.96 near to 1, overshoot almost 0. That is the original system. Okay? But for this study, just to answer for this question, we want overshoot 20%. We want to design K so that we achieve overshoot 20%. So what we do, we want 20% overshoot. Then from here, we take 20% overshoot. We know the zeta. Zeta is 0.4, about 0.46, 45 actually. Okay. So we want zeta 0.46 in order to achieve overshoot 20%. Zeta 0.46 here from the second graph, 0.46, we can calculate for, we can obtain the desired phase margin is here. is about 48 degrees. Zeta 0.46, phase margin 48 degree. So this is the desired phase margin. In order to obtain overshoot 20%. What should we do in order to get phase margin 48 degrees? Then we go back to the graph, the box plot. I replotted again here. The box plot, the same one. If you have this, please use it. I'm sure it's good if you printed, as I mentioned earlier. So now we want overshoot. We want a phase margin 48 degree. Let's see the phase here. Desired phase margin 48 degrees. Okay, so we know that the phase that we want is 140 minus 48. It's 132 degrees. 132 degree. 132 degree is about here. 135 maybe here. Just the scale. Okay. 132. Let's say this is minus 132 degrees. So here. So here. 132. And frequency is about 2.8, let's say, radian per second. This is just estimate. I just estimate 2.8. Here 2. Then in between 2 and 3. Let's take 2.8. Then this is the gain margin, the phase margin that we want. Okay, is here. 180 minus 132, then we get phase margin 48 degrees. So, therefore, at 2.8 here, 2.8, let's say this is 2.8. The gain here must be at 0. We want to make sure all the magnitude all increase so that it will be like this. And here is 0. Okay, that they are in parallel, the same. We want to increase the magnitude by this value, so that at this point, at 2.8 radian per second, the magnitude is 0. If we can make this, then we can get phase margin 48 degree. Then we can get overshoot 20%. How to do that? We need to increase the gain. We need to increase the magnitude by this dB. This is 1, 2, 3, 4, 5, 4, 12 dB. This is minus 12 dB. So we need to increase by 12 dB. All. Okay, remember K, when we change K, all will be shifted up and down. If we increase, it's going up. If we reduce, going down. But if we will parallel, all will be shifted. So here we want to shift by 12 dB because originally it is at minus 12. We want to add 12. So that becomes 0. That means 20 log K1, I use K1 here, equal to 12. We want to add by 12 dB. So K1 is anti-lock 12 minus 20. It is 3.98. K 3.98. K1 here. From the question, initially, the K used to plot the dot plot is equal to 1. Therefore, the final K is 1 multiplied with 3.98 is equal to 3.98. Okay? If originally they use different value of K, then we have to multiply here. Okay? So if we use K 3.98, all will be shifted by 12 dB. Then we can make sure the magnitude at 2.8 radian per second will cross 0 dB in order to obtain 48 degrees phase margin. Any question on here until here? Any question, or can you understand?
No question, Doctor.
Right, let's do another example. Number 5. Okay, for another application, the original system in A, now we go back to A, okay, must operate with a gain margin of 40 dB. Now we want gain margin 40 dB. Design a new K for this. Design a new K to achieve this objective. Explain the effect on the steady state error with the new K. Another question. Now our aim is 40 dB gain margin. Right? Gain margin, our original gain margin is 26 dB. We want it to be 40 dB. We know gain margin when it is 180 degrees here, 180 degrees, 80 degrees, we look into here, it is at 7 radian per second. This is the phase crossover frequency at 7 radian per second here, at 7 radian per second. We look into again the 7. So yeah, 7. We look into here. It's about 26 dB. Okay, so original gain margin is 26 dB. We want to make the gain margin as 40 dB. Desired gain margin 40 dB. How to do it? We can shift the magnitude up and down. In this case, we have to make sure it's going down because we want to make it 40 dB. We want 40 dB. That means we want the magnitude cross this point at 7 radian per second. That means we want it is something like this. all shifted down. So that will be like this. Okay. And how many we want to shift is this value by this gain. It is initially 26. We want to make it 40. Then we reduce by 14 dB. Here the difference is 14 dB. So that we finally get 40 dB gain margin. How to do it? Again, the same procedure as the first one. 20 log K. 1, I use K1. But now we want to reduce. That means minus 14. We reduce from 26 become 40. So we reduce by 14, minus 14. So when we reduce, K will also, we will use a smaller K. K1 is anti-log minus 14 over 20. It is minus 0.19 or minus 0.2. Minus 0.2. So now K can be multiplied with 1. 1 is the original K. Therefore, K is 0.2. K 0.2 will make the system gain margin 40 dB because we reduce. Now you can see that when K more than 1, it will increase, it will go up. When K less than 1, it will going down. So K less than 1 will give negative dB. I mean log K. When K K less than 1, log something which is less than 1 will give negative. Any question on this? This is actually similar concept. First, designing phase margin. The second one, designing gain margin. The question again asks, explain the effect on the steady state error with the new gain. We can see that when we shifted the magnitude down, now the kV, remember kV is this is kV. kV will change. Now kV becomes here. This is kV. 0.01, maybe 0.1, 0.00, maybe 0.17 kV. kV initially it was 0.8. Original kV 0.8. New kV is 0.17 because we shifted down. When kV reduce, that means error. Error 1 over kV. When we reduce kV, that means error will increase. Error now 1 over 0.17. Okay, it's quite high. It was 1.2. Now it will increase. 5.8, 5.9, 5.88. The new error. because we reduce the magnitude. Okay, that is the effect on reducing the magnitude going down. But if we increase the magnitude here, for the first case, error will increase. Sorry, KV will increase, error will reduce. So that means there is a relationship between error and the magnitude. And we call here is magnitude at the low frequency. Because the one which is important is at low frequency, at this region. Number 6, in a more complicated control task, the control system is required to operate with a 10% overshoot and 1/3 improvement in the settling time. So now the question wants to achieve two objectives. First, overshoot 10%. Secondly, settling time reduced by 1/3. Using a box plot, discuss whether the gain adjustment method can be used to achieve the objective. Okay. This is not. This is just explanation, no calculation. Actually, once we complete frequency response technique in control design, you will know that gain adjustment cannot be used to achieve two objectives. Here we in number 4 and 5, the objective is only one, either overshoot, that means phase margin, or here gain margin 40 dB. We cannot use gain adjustment to achieve overshoot at the same time to achieve gain margin. Cannot be done. It cannot be, because it will shift all. You cannot change. You can change only once. So that is the disadvantage of gain adjustment. It is easy, but can only be used to achieve one objective. If we need to achieve two objectives, then we need to design another controller. Here we have lead controller, select controller. You can imagine gain adjustment similar to just KP in PID control. Only one, only KP, only P controller. Then you can achieve only one. So we have done a gain adjustment. Any question on this before we proceed to another controller? Any question regarding this example? Can you understand? Question 5. Najiha asked to repeat question 5. Which one? Gain margin or error? Najiha. Error. what we did just now, remember, now we are discussing about error, the effect on the error. Okay? This is the original one. Original, how to get error? Because this is system type 1. Type 1 will be like this. We'll start with a slope 20 dB per decade, minus 20 dB per decade. So how to get error is by making a line, a straight line to here, to 0 dB. Then here is kV, and error is 1 over kV. Using this technique, we can make a line here, a straight line. You need a straight line. But for this example, it is somehow already a straight line that already touched cross 0 dB. At here 0.8. So that means the original here, kV is 0.8, and error is 1 over kV is 1.2. That's the original system. Now, for question 5, we need to achieve 40 dB phase gain margin. Then we need to reduce. So we need to reduce so that it will be like this. Okay. I didn't calculate. It should be reduced by 12 dB. I just make like this. No. This is not that accurate, but we need to reduce like this by 12 dB. So what happened when we make a new magnitude? I can again calculate kV. We make a line here. We get new kV. Okay, kV. In this example, kV 0.1, 0.2. Okay. New kV mean here kV 0.2 and error will be 1 over 0.2, will increase. The actual one here, we say kV 0.17 something. Okay, this is just another example. Just to show you, when we reduce the magnitude, the kV also reduce. And when kV reduce, error will increase. If we also consider the question number 4, in which we increase the magnitude. This is question number 3 and number 4. When we increase the magnitude, now kV. If we check the kV here, I can make line, a straight line. This is kV, new kV, which is now about 1.234. kV equal to 4. This is just example. I mean, maybe not correct when compared to question number 4. I just make to show that when we increase, then we can get new kV. Then error will be 1 over 4, 0.25. Then we reduce the error. That means kV or error is depending on This part. Okay, the one that cross 0 dB. And must be using this. We also have error based on type 0 system and type 2 system. Please look into it also in the notes. How can we calculate error for the other types based on or using bot plot? Okay, we will take a 10-minute break. We will continue at 8:55. I will continue with the first controller today with the lag compensator. We have two controllers, lag compensator and also lead compensator. Today we will start with the first one, the lag compensator. We take a 10-minute break and we continue at about 8:55. Let's start with the first controller, which is the lag controller. Later you will see why they call lag. Lag compensator, normally in time domain we call controller, P controller, PI controller, PID controller. In frequency domain, it is normally used as compensator, but they are actually the same, is to control, to achieve certain objective. Lag compensator is used to improve steady state error. Okay, if we want to improve steady state error, then we will use lag compensator without affecting the transient response. Transient response meaning here is the overshoot, rise time, settling time, peak time. We will improve steady state error but maintaining the transient response. How can we improve the steady state error? We can improve the steady state error by increasing the low frequency gain. Remember, before break, we discussed about error, about static error constant, about KV, for example. And KV is related to the, if I can draw again here, this is KV. In order to achieve a better error, that means a lower error, we need to increase KV. So error equal to 1 over KV. We want to have a higher KV. How can we have a higher KV? We can achieve by changing the magnitude at the lower frequency, at low frequency. If I can increase, instead of from here, it will be like this. Then perhaps the rest is the same. This is new KV. New KV with lower error. We reduce the error. This is what we mean by improve the steady state error by increasing the low frequency gain. This is the low frequency gain part. Low frequency gain. That's the first one. The second one is to increase the phase margin. to yield desired transient response. Later you will see when we improve the error, the transient response will slightly be changed. Then we need to achieve the original transient response by designing the phase margin. Okay. So that is lag compensator. I will erase this. I need to use display letter. When we say lag compensator, this is the transfer function. GC, C here denote the controller, S plus 1 over T. Divide by S plus 1 over alpha T. And alpha here always greater than 1. So here alpha greater than 1, that means 1 over something which is bigger than T, because alpha more than 1. So if I plot the magnitude of the lag compensator, it will be something like this. We will see later why because here is 1 over T, here is 1 over alpha T. So it will be like this. This is 0 dB. And we plot the phase. The phase will be something like this, which is here minus 90 degrees. This is 0 degrees. We cannot 1 over T is here. 1 over alpha T is here. Is 45 degrees minus 45 degrees. This is why we call this compensator as the lag compensator. Lag meaning here it is lagging. It is negative here, minus 90 degrees. Okay, this is the one that refer to. This is why we use lag we call lag compensator. It's here minus 90 degrees. You will see later. For the other one is in contrast. We call lead compensator later. This is the theory. How can we design the lag compensator? The first one, first we need to only see the uncompensated system. Uncompensated means without a controller. Here, uncompensated system. Okay, first see the uncompensated system. The uncompensated system is unstable. So first, we actually design we design the KV. Okay, we increase KV. Because we increase kV here, we get this is kV what we desired kV. But because we increase the system here, if we check the uncompensated system 180 degrees, check here, it is unstable. The system is unstable because at minus 180 degrees, it is positive. The magnitude is positive. The system, the original system is unstable. Why unstable? Because we increase the gain. Why we increase the gain? Because we want to achieve the kV that we want. That means we want to reduce the error. We increase kV, but because we increase, it is unstable. Okay, this is the lag compensator. The lag compensator reduce the high frequency gain. High frequency mean at this point, low at high frequency, while maintaining or not changing the low frequency gain. So we have high frequency, we have low frequency. What we will do is we want to make the system stable. So we reduce. Now let's see, this is the compensated system. Okay. So now by using lag compensator, this is lag compensator. As I show, it's like this, lag compensator. This is lag. By using lag compensator, we can reduce at this point. See, initially unstable, now become stable. And this is lag compensator, the phase. Now the compensated system is the blue here, the blue here. Now 180 degrees is the system is stable, and we can achieve the desired phase margin. Maybe here this is the desired phase margin. We can achieve and making sure that it cross 0 dB at this point. That is on the high frequency gain. In contrast, in the low frequency gain, we will try to make sure that it can be maintained, so that we can achieve the desired kV. How to achieve that? You can see here the lag compensator has 0 dB. 0 dB plus the original one, that means we can maintain the compensated system same as this. Then we can get the kV that we want. But we can make the system become stable and also achieve the desired phase margin. How to do that? As I explained, we will maintain magnitude at low frequency and modify the high frequency gain. And this is done by the lag compensator here. Our task in lag compensator is to design this to obtain the one here. To obtain all the values, then we can get the transfer function. Okay, it is actually quite difficult to understand, especially through online. Hopefully, we can gain more understanding by doing some examples. And of course, this one you need to practice. You have to do hands-on on the paper, on the semi-log graph paper. Okay. If you just see, it will be quite difficult to understand. This is the step in designing. I will skip this one. You can read this letter. Once you understand how to design, you can re-look into this again. I want to move into an example. Hope that it can increase the understanding on designing a lag compensator. We have one example. This one taken from the textbook. Then we will have this is another example taken from the textbook. I give the answer. Then we will do a few past year questions. 2014-15, 13-14, two past year questions. Hope that we can improve. Hope that your understanding can be improved by doing those examples. Let's do the first one. Okay, given the system, use block diagram to design a lag compensator to yield a 10-fold improvement. We want to obtain 10-fold. 10-fold meaning 10 times. Fold mean time. 10-time improvement or 10-fold improvement in the steady state error over the gain compensated system while keeping percent overshoot at 9.5%. So we want to improve error but maintain percent overshoot at 9.5%. If you look back into previous example in the gain adjustment, this is actually the same question, the same system. I will go back to the question. See the same in your slide. Also the same here. We want 9.5% overshoot. We want to design K. This is for gain adjustment. Right? We will use this, and K that we obtain is 583.9 to achieve 9.5% overshoot. Okay, 9.5% overshoot. K 583.9. You can refer back to the previous note. But of course, we also did on our own. We get about 568. Okay, this is based on the accuracy. But the actual one, this is from the book, is 583.9. So we use that one, 583.9. Right? From the previous example, to achieve 9.5% overshoot, K is 583.9. This is the original system with percent overshoot, 9.5%. So I can rewrite the equation. GS equal to 100 100K, S plus 36, S plus 100. And K is 583.9. Then we get 583,900. Our S plus 36, S plus 100. That is the system. If the system with overshoot 9.5%. We can calculate KV. Okay, remember, KV can be obtained from the plot, can also be calculated. Of course, if we calculate, it will be more accurate. So KV is limit S to 0, SGS. We will get, if you substitute the value, 583,900 divided by 3600. It is 16.22. That is the KV, and error is 1 over 16.22 is 0.062. We call this as the original system. Let's continue to design. We want tenfold improvement or 10 time improvement. That means we want error become 0.00062 divided by 10, because we always want to reduce by reduce error. That means we reduce, we must divide by 10. Okay, it will be 0.0062. This is our desired error. Or similarly, KV is, we multiply KV with 10. 162.2. The same, if we error is 1 over KV, 1 over 162.2. We get the same. That means we want to increase KV by 10 times. 60.22 become 162.2. In order to achieve the desired KV, we can again calculate a new K. GS, let's say I calculate KV using the limit. It will be, if I maintain the K, 100K over 3,600. I apply KV here for GS, because I want to find K. And we want our KV become 162.2. Therefore, K is 3600, 162.2 divided by 100. You calculate, it is 5839 point something, 5839. That is the K that we should use in order to get KV 162.2. Therefore, if I rewrite GS with the new K become 5839 multiply with 100, 0, divide by S plus 36, S plus 100. Right, this is based on this. With the new K, K5839. I hope you understand until now. Any question before we move?
No, sir.
Okay, also, I wrote also in your slide the same here. Okay, let's see. Let's move to a bot plot. This is a bot plot for GS equal to 583,900 over S plus 36, S plus 100. Maybe not in your slide. Because I just I added this after that to I mean, so that I hope that you can I hope that I can explain better with this. You are given this one. This is the same as the, let's see, the uncompensated system. I redraw the uncompensated system so that it is clearer, because this one they combine both uncompensated and compensated. So in your slide, it will be similar to the uncompensated system. I also plotted according with the same scale from 0.01 to 100 in the omega, radian per second. Omega, radian per second. With the same for decade here. So this is the original the system with K here. If we check KV, of course not so accurate, but KV here, if we check, if I make line, a straight line from here to here, okay, to 0, this is 0, this is KV. KV may be here. Okay, KV should be, this is 10, this is 100. KB should be 162, should be here, should be 100, 200, should be here maybe. Okay, 162.2. If we check this one, perhaps clearer this one. If you check uncompensated, you make line, this is 0 dB, you make line here. Here is KV, 162.2. Of course, you will not get 162. I mean, because of the accuracy. 0.2, of course, you cannot get. Yeah, maybe you will get 160. And also we have only 100, then 200. So in between 100 and 200. That is KV, 162.2. Okay, we already get KV, 162.2. Remember that we want KV 162.2. Then we want overshoot 9.5%. Although we already obtained initially 9.5%, but because we changed K, okay, remember, we get 9.5% with K 583.9. But because we want to improve the error, we change K, become 583.9. Of course, the overshoot will now change because we use different K. Okay? Then we have to return back to design so that we can maintain overshoot 9.5%. How to do it? We 9.5%, we look back into this. Okay, 9.5% overshoot, about 10% here is 0.6. Zeta, we record 0.6. 0.6 zeta here, given about 60 degrees. Phase margin about 60 degrees. In order to obtain overshoot 9.5%. You have to be familiar with that. In order to get overshoot 9.5%, we need phase margin 60 degrees. Currently, if we check the phase margin at here, phase margin when 0 dB, here, we will not get 60 degrees. It is actually here, not 60 degrees. We have to design so that we get 60 degrees. How to get 60 degrees? We have to 60 degrees mean here 120. This is, I just show here 120. Right? And I'm sure this. Okay. With K535 5839, we can achieve KV equal to 162.2. I will write what I have what I explained just now. However, the original overshoot and phase margin has been changed. Okay, original overshoot here is 9.5%. I will write. So that is why we want to design a lag compensator. We need to maintain the original phase margin, original overshoot and phase margin, which is overshoot is 9.5% overshoot and 60 degrees phase margin. All right, based on the graph, we know that in order to get in order to get 9.5% overshoot, we need to have phase margin 60 degrees. In design, in frequency response design, based on observation, we normally need to add what we call a correction factor. By example, by adding 10 degrees. Based on observation by many, they have studied many, they have designed many lag compensator and also lead compensator. It is found that we may need to add a correction factor. This is of course not compulsory. If you add also not so accurate, but it is advisable to add a correction factor. So therefore, that means the desired phase margin is 60 degrees plus 10 degrees, 70 degrees. Okay. In order to obtain 60 degrees, it is advisable when designed, we add a correction factor of 10 degrees. But if you did not add also, it is acceptable. But in design, once we have, if we use MATLAB, then easy. We can just try. We can add 5 degrees. We can also did not consider correction factor. We can add 10 degrees, we can add 15 degrees just to see whether we can get what we want. Okay. In the exam, it will depend. The question will mention to you adding correction factor or not. Okay. But the formula, the procedure is the same. But you just add 10 degrees if required. So let's see, we add 10 degrees. That means we want 70 degrees phase margin. 70 degree phase margin means if I go back here, I want 110 because 70. Our interest is at 110 degrees. 90. Maybe here. I just, not so accurate here. Maybe minus 110 here. So I make line. So maybe here. This is the one. If we take the phase margin is 70 degrees. That's why our interest is 110 degrees because we want 70 degrees phase margin. Right? 70 degrees. But how can we make sure the system now has phase margin 70 degrees? It can be obtained if at this point, let's say here 10 10 radian per second here, it cross 0 dB at this point. If I can change the magnitude so that it can pass through 0 dB at this point, then I can get phase margin 70 degrees. In gain adjustment, we can also obtain 70 degrees by, if I reduce all, like this. I reduce all, I shifted the gain, shifted the magnitude by the same dB. In this case, I reduce. But what happened? If I reduce, KV will also change. Okay, now different KV. KV may be here. Cross 0 dB, maybe here KV. But we want this KV. This is our desired KV. That's why gain adjustment cannot be used. Because gain adjustment, as I mentioned earlier, can only achieve one objective. In here, I can achieve 70 degrees phase margin. But the error will change. But our intention is to get, our aim is to have 162.2 kV, phase margin 9.5, phase margin 60 degrees. So they overshoot 9.5. Therefore, gain margin cannot be used. So you will change all. You can change both. Then what to use? This is where we can use LED compensator. How to design LED compensator? First, we need to know this value. Okay, because we want to make it 0. So if you check this value, here is about 24 dB. Okay, you can also check here. It's about 24 dB here. 24 dB. Okay, when it is 110 degree. Okay. It is shown here. 110 degree, 24. It is 24 degree. Right? I want to show here first. So how can we make sure it is 0 dB here? It can be done by adding a LED compensator with the magnitude here is minus 24. So that 24 plus minus 24 becomes 0 dB. That is the first part of the LED compensator. Okay, how can we proceed to design? To proceed is we take the frequency here, let's say 10 radian per second. We will, our interest is 1 decade after that. Before that, I will use the correct one. In the book, it is, sorry, not, this is 1. Okay. In the book, it is 9.8. I will use 9.8. Okay, although, as I mentioned, it's not accurate. the one in the book is 9.8. It's about 10 here. I will use 9.8 radian per second. 9.8 when it is minus 110, minus 110 degrees. Okay, our interest in design, how to design, if initially 9.8, we will go 1 decade before that. Here is 1, here 0.1. We will go 1 decade before 9.8, which is 1 decade means 0.98. Here, 0.98. We make a line until 0.98. We make a line 1 decade from the initial point. That means it is minus 24 dB. Then we proceed. We need to make a line until 0 dB. Okay. A line of like this. A line like this. This is minus 20 dB per decade. You can use a ruler. You can. You have to. You must have. You must know the slope. Minus 20 dB per decade. Then you make a line until 0 dB. And we know this point. This point to this point must be minus 20 dB per decade line. How you can do you have to practice this using the semi-log graph paper. I could not show here because the scale. You can let's say how to show. If you have a graph paper, what you can do, you can this is 1 decade. This is let's say this is minus 20 dB. This is a slope of minus 20 dB per decade. 1 decade is reduced by 20 dB. Then you can use this slope to plot this one. It will be parallel line, because they have the same slope. Okay, then after that it will be 0. This is lag compensator. With this, we can make sure this point go to 0 if we add these two. We can make sure this point go to 0. Then we get phase margin 70 degrees. And the other, which is important, is we can make sure KV is maintained. Why? Because here, initially, is 0 dB. It's not similar to gain adjustment where all change. Here, the magnitude here is 0 dB. Therefore, if we add with the original one, we will get the same magnitude at the low frequency. Then we can get the same KV. So that is LED compensator. It change magnitude at the high frequency, maintain magnitude at low frequency. And the point here is important. This is the break frequency, because the break frequency will be used to determine the transfer function. If this is 9.8, here is 0.98 radian per second. And this is depending on the line that you make. It will not be 0.098 because it is here 24 dB. If 20, then yes, 1 decade becomes 0.098. If you do it, it will be 0.062. The point here. Okay, I know it is important. It is difficult to understand, but we proceed first. So the point here 0.98 and 0.062. Therefore, we redraw here. We start by here at this point, 9.8 radian per second. This is minus 24 dB. Here until 0.98. Then we make a line, minus 20 dB per decade. Then we get this, and then after that is 0. And this point is obtained from the graph as 0.062. This is the LED compensator. And those values are important because DC, the controller, the transfer function, is actually a combination of two transfer functions, two systems, or two components. First is this. If you understand, if you remember about plot, it is actually first one. This is the first one, and the second one is this. If you add 1 and 2, you will get number 3, which is the LED compensator. And the break frequency is these two. The number 2, number 1 is the numerator. It is S over 0.8 plus 1. Remember, we have S over A plus 1. A is the break frequency. Here, break frequency is 0.98. Divide by, because number 2 is denominator, S over 0.062 plus 1. This is the transfer function. We can, from here, we can rewrite in another term. I can take 1 over 0.98 outside. So that is S plus 0.98. Similar here, 1 over 0.062, I can S plus 0.062. If you multiply, you get the same. And if you proceed here, it is here 1.02 S plus 0.98 divided by 16.12 S plus 0.062. And finally, the transfer function is 0.063 S plus 0.98 S plus 0.62. 0.062. That is the transfer function for the lag compensator. If we compare with the original lag compensator, you see is if you go back, you get S over 1 plus T over S plus 1 over beta alpha T. We can always equate to this. That is the transfer function for the lag compensator. I will stop here. I will continue with this example, and also we will do. I will show also here to make it clearer, and we will do some example in the next lecture. So in the next lecture, please print the dot plot for the given in the slide. Please print magnitude and phase for both questions. Okay, so that we can do together during the lecture. Okay, I will stop here. See you tomorrow. Before that, any question?
No, Doctor.
If not, thank you very much. Assalamualaikum. Good morning.
Thank you, Doctor.
Thank you, Doctor.